Hi everyone, thank you so much for joining us for the Arm SystemReady and the UEFI Firmware Ecosystem webinar. We'll get started in just a few moments. Thank you. Hi everyone, thank you again for joining us for the Arm SystemReady and the UEFI Firmware Ecosystem webinar as part of the UEFI 2021 Virtual PlugFest. I wanted to take a minute here to introduce you to our presenters today. We have Dong Wei, who is an Arm Fellow, and then we also have Samer El Haj Mahmoud, who is a Senior Principal Architect at Arm. And I will go ahead and pass it off to the presenters.
Okay, thanks. I will be talking about Arm SystemReady first, and then hand over to Samer for the Arm UEFI Firmware Ecosystem talk. Let me firstly talk about the Arm SystemReady, which was launched at the Arm Dev Summit in October last year. The purpose of the program is to basically realize the vision, letting the software to just work on ARM-based devices. So instead of each silicon vendor vertically integrating hardware, firmware, and software application stack, we would like to see common OSs being able to land on the firmware and hardware devices developed by different silicon partners and OEM ODMs. We used to have this Arm Server Ready program, and we are basically extending the success of that program to the embedded server and IoT markets. To make this possible, we want to make sure that the systems are developed following a minimum set of hardware and firmware requirements. And these requirements are reflected in a few specifications. So the BSA, the base system architecture, documents the minimum set of CPU and system architecture necessary for the OS to boot and run. This includes a lot of the guidances on PCIe integrations and so on. And we also have segment-specific supplements to deal with market such as the servers and so on. And for the firmware side, we have what we call the BBR, the base boot requirements. That is also documenting a set of minimum common firmware interfaces. But we also recognize that different software stack may require different recipes. And then we also have a test suite called Architecture Compliance Suite, ACS, that is being used to test the devices against these specifications. And we have a certification program called the Arm SystemReady. The information is available from that URL listed down below. And so speaking on the firmware side, basically we have common interfaces on ARM devices, such as PSCI and SMC calling conventions, right? These are common across the board. But on top of that, we leverage the industry standard interfaces such as UEFI, ACPI, SMBIOS, and device tree. And then, as I mentioned, we create different recipes tailored to various different OSs. So the first one is called the SBBR. This is the requirements that we have used previously for the server side, but this is not just for servers. This is actually tailored for a set of operating systems that are requiring UEFI, ACPI, and SMBIOS interfaces. But we also have environments where ACPI may not be required. But we expect the devices to have UEFI, and then that's called the EBBR. And then we also have a scenario where some of the hyperscalers want to use Linux boot as their firmware implementation, and we created this recipe called LBBR. And some of the information about the EBBR spec and the discussion channel is also available here. The spec for BBR is also listed down below. These are all public specifications. We also created this document called Base Boot Security Requirements. This is basically combining additional requirements related to the secure boot and firmware updates, as well as the measured boot using TPM. And this is also documented in the spec that the URL is provided below. And we have the additional security option for the certification. If a device implements to these interfaces, we are developing the test suite to test devices against this specification. And if it passes, we can add the security option on top. So the reason we are creating these different recipes is basically illustrated here in the system firmware landscape. We know a majority of the devices that are running the horizontal market today, for the OSs like VMware, Red Hat, Windows, and so on, these would require UEFI, ACPI, and SMBIOS. So that's why we created the SBBR recipe. Some of the OSs like Ubuntu, SUSE, and the various BSDs can also support this model. But in addition, on the left-hand side, we have a significant amount of devices that traditionally have been using Uboot and device tree for the OS launch. And we created this EBBR recipe that basically requests the developers to put UEFI interfaces on top of Uboot, which is actually supported now in the Uboot mainstream. And if you have that ABI, UEFI ABI on top of Uboot, then you can also support many of the OSs, and it also carries the benefit of separating the OS and device development. And you can expect many of these Linux and BSD distros to also support this mechanism. And as I said, some of the hyperscalers on the right-hand side are expecting to use Linux boot in their firmware, so we created LBBR. Okay, so for the SystemReady program itself, we actually currently created 4 different bands to cover these different scenarios. So if you are developing a server, on the hardware side, we expect the SoCs to be compliant to the BSA and SBSA document for the minimum hardware support. And then if you're supporting SBBR with UEFI, ACPI, and SMBIOS, then you can certify for what we call the SystemReady SR. And then if you support Linux boot, you can certify as SystemReady LS. And then if you're developing embedded or IoT devices, we expect the hardware to be BSA compliant. This is the bare minimum across the board. And then depending on the firmware, again, if you do UEFI ACPI SMBIOS, you would do the SBBR, and then you can certify as SystemReady ES. And if you choose EBBR, using Uboot, device tree, and put UEFI ABI on top, you can support and certify the SystemReady IR. And I also mentioned the security option that you can also certify if you implement the UEFI Secure Boot, firmware update, and the TPM measure boot. And here are some nice logos, I think, for the certification. Once your devices are certified, we issue you the logo plus a certification document. And if you may be wondering about the differences in terms of these different bands, this is kind of a simple chart to show how you can satisfy these requirements. If you're shooting for IR with EBBR plus device tree, that basically means you would have UEFI and device tree interfaces presented. And typically you would do the Uboot implementation and put UEFI ABI on top. But we don't really care whether you use Uboot or EDK2 to realize the UEFI interfaces. And then for the ES and SR, they are very similar. Actually, right now they are exactly the same. They are requiring SBBR firmware. What that means is that you would need to present the UEFI ACPI and SMBIOS. On the UEFI front, whether you present the UEFI interface through Uboot or EDK2, we don't really care. But traditionally, I think in this model, you typically use EDK2 to implement UEFI. But we have seen examples of where people use Uboot to implement UEFI and then add ACPI and SMBIOS. That's also valid. Okay, so these are the kind of the details of what each bands are requiring, right? Basically, as I mentioned before, if you're designing servers, you would want to meet BSA plus SBSA specifications. And then depending on, whether you choose the Linux boot route or the traditional UEFI ACPI SMBIOS route. This is the LS and the SR band on the leftmost or the rightmost column. And then in the middle, these are for the embedded servers or the IoT devices. A device could do either of those two or both. It's really depending on the firmware that you put onto these devices, right? Hardware-wise, it's the same BSA, and then firmware-wise, depending on which one you want to choose. There's a little bit of a caveat on the IR side. We are also allowing the 32-bit devices to be certified. These devices are still out there, but we don't have the BSA document covering the 32-bit. So if you are doing a 32-bit design, you can still certify for IR, and we're just not testing you on the hardware compliance side. Okay, so on the compliance test suite side, we currently have the ACPI versions, the ACS version 3.0. This was used for the server ready before, and it's currently used for SystemReady SR. It's also usable for the SystemReady ES band because the similarities between the two, right? The only difference is really the SBSA delta. And so we're in the process of constructing the SystemReady ACS for the new bands, for ES and for IR. These are under development. We are hoping to get the ACS ready by the middle of the year. And once it's there, you will see the new URL GitHub, with the content populated on the right-hand side. Right now, the structure is there. The GitHub is open, but we haven't checking the code yet. The work is still in development. On the left-hand side, the enterprise ACS is available, so you can go there. It's all open source. It will be open source for the new tests as well. So I mentioned the BBSR for the security option. So we are extending the ACS test suite to cover the BBSR requirements as well. We are leveraging a lot from the existing tools, just like the ACS, right? If you go back to the previous slide, if you look at the ACS components, we are leveraging a lot from the existing UEFI SCT. That is open source, right? It's developed originally from the UEFI forum, and also we're leveraging the FWTS that's developed from Canonical. Similarly, on the BBSR ACS, we are leveraging a lot from the existing tests from SCT and FWTS as well. And we are also going to add more test code to basically fulfill the need that we have for this security option. Okay, the other thing I want to also mention is that if you use UEFI in I think at least 3 of the 4 bands, right, you need to have UEFI drivers, and we require UEFI drivers to be in the UEFI AArch64 native format for ARM systems. Some of the ecosystem partners already provided the AArch64 binaries, as shown here with the logos. And we have a web page that shows where you get these binaries from. And we want to call the ecosystem to make more of these drivers available to support the ARM SystemReady compliant systems. Okay, with that, I'd like to hand over to Samar to continue the discussion.
Thank you, Dong. So we'll continue the presentation talking about the ARM UEFI firmware ecosystem and some of the projects and devices that are available today. We start by, of course, highlighting the TianoCore UEFI project, which is one of the main code bases that implement a lot of the UEFI standards that the ARM SystemReady program, specifically the SBIOS firmware recipe and specification, are built on top. That includes the UEFI specification itself, the ACPI, SMBIOS, the implementation of the UEFI shell, which is used as part of the certification suite, the ACS test suite, etc. So TianoCore project is important for at least the SystemReady SR and ES and the overall SystemReady testing suite. ARM and the ARM ecosystem partners and community developers are actively engaged stakeholders and participants, maintainers, contributors in the various projects in TianoCore and the EDK2 and EDK2 platforms, but also the UEFI SCT project, which is one of the main components for the ACS certification test suite. You will see here just a highlight of some of the many ARM partners and ecosystem players that are active, from ARM and Linaro to server companies that have been starting to upstream patches and support for ARM server silicon, such as Ampere and Novia. You will find embedded and edge type devices that are being upstreamed and supported by partners and companies like NXP or like the Raspberry Pi, for example. Recently, we even are seeing some drivers like what Dong mentioned available that are native for ARM64 that are also being upstreamed to EDK2, whether it's USB network adapters from like the likes of Realtek and ASICs to BMC graphics adapters or drivers from ASPEED. There's a variety of components and a growing ecosystem in this project. Another important project to highlight that's part of the ARM ecosystem support for UEFI is the Uboot project. The Uboot is a choice for many embedded and edge type platforms, starting with the historically being the predominantly vertically integrated ecosystems. It has support for many boards, a lot of them that are upstreamed, supporting, of course, multiple architectures, including the ARM64 architecture. There is a UEFI compatibility layer configuration that is built in Uboot that implements the ARM EBBR specification, allowing it to realize the minimum UEFI ABIs, boot services, runtime services, the protocols necessary for a standard off-the-shelf bootloader, for example, for most Linux distros, to load and boot the standard OS. There is ongoing effort by ARM and the community to validate the implementation with compliance testing suites such as UEFI SCT and FWTS. You can check the results by following these links and see the progress that's being made there. There are patches that are being submitted and upstreamed to both Uboot and to the test suites themselves to fill in any gaps, as well as ongoing discussion and work in the EBBR spec to enhance and again fill in any gaps that exist in terms of compliance. Recently, there is work that is happening on improving the runtime support for UEFI variables, including UEFI Secure Boot and capsule update. A good presentation on this topic was recently done by Henrik in the Open Source Firmware conference. So you can check out those slides that are linked from our slides here. Next, we are going to talk about the Linux Boot project. Linux Boot is an alternative firmware stack that is used by hyperscale data centers. It focuses on reusing the existing Linux drivers code without having to rewrite device drivers in specifically for UEFI or DXC. For ARM64 based systems, there is even the possibility of Linux Boot replacing the rest of the firmware completely, being something that can launch directly from the trusted firmware layer handed over to Linux Boot, and then Linux Boot continues all the way to booting the final OS. Of course, there is the possibility of having Linux Boot similar to what's done on other architectures, like being a target that gets loaded by the firmware. So you could still have something like a UEFI firmware that takes over from trusted firmware and then loads Linux Boot instead of, for instance, loading a UEFI shell. And then Linux Boot continues the rest of the boot process, including native device driver support to load the OS from the targeted media and boot to the final OS. one goal here is to have Linux boot being able to present the same standard interfaces to the operating system like the other recipes or the other firmware stacks that we discussed in SBBR and EBBR. You have different implementations of the firmware. It could be EDK2, it could be U-Boot, combinations, could be some commercial firmware implemented by third party. As long as the standard APIs are presented, then you can boot standard off-the-shelf OSs. So there is an ongoing effort and desire to do that in Linux boot as well. If you would like to contribute or participate, there is a link here to the Slack server channel where the discussion is happening. So you are welcome to join and participate there as well. Next, we are going to talk about some devices that follow the Arm SystemReady either certification or already certified or certification in progress, or fit in the general direction in which the Arm SystemReady umbrella is providing. We'll start with Ampere Ultra MountJ. This is a 2-socket server that is SystemReady SR certified. It's the first to be SystemReady SR certified. It's based on the Ampere Ultra processor and an 80-core configuration per socket, so you can have 160 in MountJ in a 2-socket server. Very high-end cloud native high-performance scalable CPU. The nice thing is that even though the server comes as a reference design as well as a commercially available server, comes from Ampere with commercial and open source firmware. The open source firmware is available today on public open source repository on GitHub, as well as being upstream to the TianoCore project. There is also support for Linux boot on this server with open source firmware available for the Linux boot path. And even the BMC firmware, there is an open source firmware based on the OpenBMC project that is also being upstreamed to that project. The Raspberry Pi is the next device we're going to talk about. Of course, the device itself is very popular and very available to many people. It's useful for many different applications, from very specific IoT integrated device to an edge gateway, or even a low-end developer box or a desktop machine. The UEFI code that was developed for the Raspberry Pi was done as a community project, led by many contributions from people in the community, including folks from VMware, Aki Consulting, and Arm, and others. The project itself is on GitHub with the code being fully upstream to EDK2, to TianoCore, and using open source trusted firmware code that's also upstreamed to the trusted firmware project. There is an active community around it available on that you can connect with on Discord chat server. There's a link there to join that community if you are interested, as well as a blog that has some of the behind the scenes development and updates from that community. And the Raspberry Pi is the first system that is SystemReady ES certified under the Arm SystemReady program. The NXP Layerscape 2160 LX2160 reference design board is another important system that is certified as Arm SystemReady ES. This is based on NXP's LX2160 CPU or SoC that includes 16 cores, useful for many important applications, mobile edge gateways, edge compute, 5G switching, etc. So this is the reference design board. So will be interesting to see additional products built using this design. From Arm SystemReady point of view, the device is certified and the firmware is available upstream as well as directly from NXP on open source repository. Both trusted firmware and the UEFI EDK2 based firmware is available with ACPI and SMBIOS implementation. And you can follow those links to look at the code or to download it. The next device I'm going to talk about is the solid run Honeycomb LX2K. This device is a workstation or a microserver edge gateway platform that is built by Solid Run. It uses the NXP Layerscape 2160, the SoC we just talked about, and it has a UEFI firmware based on EDK2 that is not upstream to TianoCore yet, but it is open source and available from Solid Run on open source GitHub repositories. And again, there is a Discord community that you can join and connect, including direct support and interaction from Solid Run. So I encourage you, if you're interested in this device, to check out the Solid Run website and join that community. The NXP LS1046 is another device from NXP that is going through a SystemReady program. With open source code available from NXP and upstreamed to TianoCore. Trusted firmware also available as open source. So you can see a lot of these devices, when we say SystemReady ES or SR, they end up being centered around TianoCore EDK2, either in the upstream or in other forks of their code that are also available in open source. There is a version of QEMU as a virtualization environment that is going through an effort by Linaro to make that implementation more SBSA compliant, including implementing additional requirements in SBSA for hardware components. Remember, SBSA is the server supplement to the BSA, to the base system architecture requirement or the basic hardware requirements for the SystemReady program. So SBSA adds additional server-specific requirements on top of the BSA specification. So the effort here is to try to get this platform to be more complete, that could pass the SystemReady ES or even the SR level 3 or above SBSA requirements. From a UEFI point of view, the work is also happening in the TianoCore project. You can see SBDR compliant firmware available in EDK2 with the link pointed to in these slides. With additional work, of course, is happening to fill in any compliance testing fix issues or compliance testing gaps. And in fact, the testing reports are also available directly from Linaro and linked in these slides as well. And finally, the last slide we're going to talk about today is the Marvell Octane TX2 with a board available from Solid Run. The interesting thing here is SemiHalf, a company that is experienced in firmware and OS development, have been presenting their effort to bring this device to SBDR compliance, including ACPI and SMBIOS and UEFI implementation upstream in EDK2 and in trusted firmware projects. There was a recent presentation about this from SemiHalf in the OSFC 2020 conference as well. That's linked here for reference. So a lot of activity around that fall under the general umbrella of SystemReady, whether the devices are directly already certified or certification in progress, or fitting under the general direction in which this program, the vision in which this program is trying to achieve. That's it for today. Thank you for listening. We'll stop now and see if we can take some questions. Thank you.
Thanks, Samer. Thanks, Dong. The first question that we had here is, which market segments do ARM SystemReady target?
Yeah, so right now, as I explained initially, we are targeting certainly servers, as we used to have the SystemReady program, right? So this is the either the SystemReady SR or the SystemReady LS, and we are also targeting the infrastructure edge and IoT devices. So this is using the SystemReady ES and IR to cover that market. Those are the market segments that we are supporting today.
Thank you. The next question here is, x86 emulation project is having a code to run the x86 option ROM on ARM64 hardware. However, SBBR spec clearly identifies that binaries should be ARM64 executables. Does ARM recommend this open source project for any of its recipe? If not, what are the efforts taken to educate the customers on this use case?
Sorry, I can help answer this one. Like the question states, SBBR does require the ARM64 executables, and we would like the implementations to move into this direction. So whether it's source code that is built natively for ARM64, or it's binaries loaded directly from the firmware or from the device as an option ROM, they should really be ARM64. That is the recommended direction per the requirements and the specification. x86 emulation provides a bridge for PCI devices that do not have native ARM64 drivers. So it's usable in some of these cases, but it is outside the minimum requirements from the SystemReady specifications. So it can be used to unblock some customer use cases, but it's outside the recommendation from the ARM SystemReady program.
Thank you. The next question is, how does this program benefit the ARM ecosystem partners, OEMs, and silicon providers?
Yeah, I think as I explained at the beginning, right? So the intention is to provide this what someone called the boring environment, right? So we want to make it easier for the software, operating system, hypervisors, and other software pieces to be easily landing on the ARM-based devices. So the intention is that you can just grab a standard distribution of these operating systems and hypervisors and not do any of the porting effort to your particular device, and expect these operating systems to just install and run. So that's the intention of the program. I think it contrasts with the traditional legacy way of developing devices and having to customize operating systems for each devices, that kind of environment in the past.
Thank you. And one more question here. Can an open source firmware community certify a device without involving the OEM or silicon provider?
Samer, do you want to take that question?
Sure. The specifications and the certification test suite and really all the details about the program that we presented today are available publicly from ARM. Anyone can really download the requirements and the test tools. The test tools are actually even open source, so you can submit issues and even pull requests against the test tools if you see something that's not right. So it's not exclusive to ARM partners. We do have some procedures in place and working directly with partners and collaborating as part of promoting the program and wanting to see more devices follow this program. But if there is interest from the community, the contact information of how to reach ARM, or you can contact Dong and myself directly as well. Just to point as an example, the Raspberry Pi firmware was mostly developed by the community. Some of the devices we mentioned here that are interesting activity happening by the community that are falling under general direction, which SystemReady envisions. So I hope that answers the question. If people have additional questions in this area, they can follow up with Dong or myself or Arm.
Great, Dong, Samer, thank you so much. Next, we will be moving on to a live WebEx Q&A. This is your opportunity to chat live with the presenters and ask them any questions you have. It's meant more as a kind of open conversation. So please feel free to join us there after we wrap up here. And we just want to thank you all so much for joining us today. These slides will be available on the UEFI Forum website, and this video recording of this presentation will be available on both BrightTalk and YouTube. So thank you all so much.
Thank you.